Hi everybody, this is another example of an application that involves trying to get the graph of a messy exponential function and use it to answer questions. So face-to-face classes, I would generally give students a chance to work on this in class if I have time. If you're an online student, this would be a great one to pause and try and work on, and then you can check yourself and see if it looks good compared. So we are looking at this function. This is a basic y equals 2 to the t function with what I think I see 4 transformations. So I'm going to start with my basic picture. And this is another one where the transformations like this is horizontal compression by 1 over 1.9, are ugly enough that I don't really want to follow that point by point. You can if you want to, but I want to work a little bit on just keeping track of the rough idea of what the shape is and seeing if I'm good enough at it to really figure out what the final picture is. Okay, so there's my 2 to the t. I see vertical stretch. So we're going to double more than that. Our base is 2. We're going to multiply all our y values by 20. So our vertical scale is going to get really big. For example, if we wanted to follow a point, 0, 1 would stretch all the way up to 0, 20. But I haven't labeled scale or anything, so I'm just going to keep track in my head of the idea that my y values are pretty big now. I've stretched it up and it's pretty darn tall. I see this horizontal compression. So it's roughly by 1/2, but not exactly, which I've already stretched it vertically a lot. Horizontal compression at that point is going to make it even steeper. So I have a really steep graph that has fairly big y values. I also see a flip. That's attached to my t, so that's going to be a flip over the y-axis, horizontal flip. And then I see a shift up, that's not up in the exponent, so that's affecting y's, 75. Okay, so vertical stretch, horizontal compression, again, since I haven't labeled any scale on my axes anyways, I can just kind of keep track in my head that makes my y values get really big really fast. The flip does change the general picture in my head. So flip across the y-axis doesn't change the horizontal asymptote, but it will flip-flop me going this way. That looks a little skewed, but that's okay. General shape is now it's decreasing to its asymptote. And the last thing I have is the shift up 75. So that will move my asymptote. That's definitely going to be important to me. That's a really crooked looking axis. Okay, so let me leave myself some room. Let's say this is y equals 75. So what's important right now is to realize I've shifted this all up. So my graph is starting up at positive infinity and coming down and approaching the horizontal asymptote. I don't think I've said yet what this situation is. So if you haven't read it, this function is telling me the face of an iron. I don't think I gave you units, but it's supposed to be telling you the temperature of the face of a household iron, where T is the time in hours since it was turned off. And I'm using degrees Fahrenheit, so bad me for not giving you units, but this is temperature in degrees Fahrenheit, T hours after someone turned off their iron. So you're ironing clothes or something like that, and it's cooling. So I like the fact that it's starting up here somewhere and it's decreasing. That should be what's happening. So this is my general picture. And again, I think it would be really helpful to know exactly where this is. That would tell me a lot about what's going on. So to get that, you can again try to follow this y-intercept 0, 1 through all your transformations. I actually think again in this one, since we don't have any horizontal shift, that would probably work for you. But your other option is to just plug 0 into the final equation. So if t is 0, I get 0 in the exponent. 2 to the 0 is 1. So I'm getting 20 times 1 plus 75, which is 95. So I have a y-intercept at 0, 95, and then my y values decrease to 75. I can check this on my calculator again. Okay, so I had 20 times 2 to the negative 1.9x plus 75. And I'm going to go into my window. Let's see, hours since it was turned off. I would think it wouldn't take very long to cool off. Let's look at, I don't know, 5-6 hours, something like that. Y's, we need to see more than 0 to 11, so I'm going to raise my y max to 100. I'm going to keep my y min at 0 because that's what I'm looking at here. I see the x-axis, and then I want to see all the way up to above my y-intercept. So let's try that. That's looking pretty good. And if you really want to confirm, we claim that our horizontal asymptote was at 75. You can put that in your y2. And that looks great. That looks right like where my graph is leveling off to 75. So I'm feeling pretty good about this. This was 6 hours. I don't even think mine looks like I'm not seeing that much. Mine looks like I'm seeing a littler chunk. So let's just say this is like 4 hours worth of the graph. Again, that doesn't have to be super perfect, but give me the general idea of how much of the graph you think I'm seeing here. This is hours, and this is degrees Fahrenheit, the one I forgot to write in the problem. Okay, so there's my graph. Again, from here, I hope that the rest is actually pretty easy. If you can get a good picture, I'm hoping it's really intuitive to answer these questions. So first question is find f of 0 and explain its meaning. We've already done the find part. F of 0 is 95. So plug 0 into f. I guess it's a little f. The meaning, this means that at t equals 0, so right when the iron was turned off, its temperature was 95 degrees Fahrenheit. So that's how hot it was heated up to. When it was turned off, oh, this is less than legible today. The temp of the iron was 95 degrees Fahrenheit. Okay, so y-intercept, that was the initial temperature of the iron when it first started cooling. Horizontal asymptote, find and explain its meaning. Again, we've already found the horizontal asymptote. We followed the transformations. We know it's at y equals 75. If we want to explain what that means, we have this iron unplugged sitting out cooling, and it's cooling down to 75 degrees. So I would say that that's probably room temperature in this house. So I do want to be a little careful in my wording of this because the horizontal asymptote is not actually just about y's. It's about what y's do when t's in this case get big. So what I know is that as t gets really, really big, y drops to 75. So to explain that, I'm going to say the temperature of the iron is decreasing to 75 degrees Fahrenheit, and then I'm just going to make a little note that that seems to be room temperature. Okay, last one, estimate when f of t is equal to 80 and explain the meaning of our solution. So this should be 80, so 95, so it's just a little bit above this. So somewhere in here. And we can use the calculator for this. So we don't have the tools to actually set our y value in our equation equal to 80 and solve. We'll get them shortly, but right now we don't have them. So this would be a trial and error or calculator question. You can just plug into this equation, but I would say if you've got the graph in front of you, that makes that really quick because you can go back to this trace tool. So 3 hours is too long. I'm already down to 75. Let's go 2 hours. 76, still too long. 1 hour. 1 hour is close. Just over 80. 1.1 hours. Ooh. Okay, so it's right. Let me decide which was closer. Between 1 and 1.1. I'm fine with 1/10 of an hour, but I'm just going to go right in the middle and say after about 1.05 hours. So t is approximately 1.05 hours. So again, it's fine that that's a trial and error for now. After we learn about logs and go through solving exponential and log equations, we'll come back to some problems like this and we'll actually solve them algebraically. Explain the meaning. So what this means is that the temperature of the iron drops to 80 degrees Fahrenheit in just over an hour. All right, thank you for watching.